Today we're going to look at factoring polynomial expressions. There's several strategies and things that you can do when factoring polynomials. The first thing that you should always do is look for a GCF. So when looking for a GCF, the question we're asking ourselves is there a number and or variable that will factor out of every single term? So it's not just the number, it's not just the variable, we need to look at both. And if we do have something that we can factor out, we need to do that first. When we factor out a GCF, it's really important that you also include that in your final answer. If you factor out a GCF and then fail to write the GCF in the rest of your factorization, your answer is incorrect because you've left out something that needs to be multiplied to get back to your original term. So make sure if you factor out a GCF that you don't just drop that out of the problem and don't continue to include that in your answer. After you factored out your GCF, then you want to ask yourself, how many terms am I working with in the polynomial to factor? Because that will send you into some different strategies that you can use. Again, there are so many examples and so many possible ways that you could use these strategies. There's no way that I could get all of that information into a single video. I would be filming factoring videos for the rest of the year if the goal was to show you every example. The goal of this video is to show you the strategies that you can apply to different problems. So again, back to the point of we're going to look at the number of terms. If we have 2 terms, 3 terms, or 4 terms, we're going to be using different strategies to factor those polynomials. The first one we look at is 2 terms. So the most common type of problem you'll have that has 2 terms is what we call a difference of squares. Squares meaning perfect squares or variables that are squared. So x squared, b squared, t squared, doesn't matter the number. Difference, so we're subtracting, and then a number being squared. So you need to make sure that you've memorized all of your perfect squares up to at least 15 to help you with a difference of squares problem. So we can look at this problem, x squared minus 64, and again, the x is being squared. 64 has a perfect square root of 8. So when we factor that one, we're going to look at the 2 things being multiplied together and using those. And then I'm going to go ahead and put the second example up there so that it's easier for me to write on the screen. But for the second example, we're going to have to look at that GCF. On the first example, again, we said that we're using 2 terms. So this goes back to things that you would have learned in Math 1 and Math 2 about factoring quadratic expressions. So a difference of squares, we take the x. One of them has to be a plus and one has to be a minus, because when I multiply these out, that middle term needs to cancel each other out. So your Math 2 teacher might have taught you different strategies like using a box or the FOIL method for the distributive property. But again, if I were to take and multiply these 2 things together, then I would end up back with what I started. In the second example, again, we're going to look for a GCF first. I can factor a 2 out of both of those terms, and I can factor an n out of both of those terms. So I have n to the first and n to the third. So we factor out the smaller exponent. 2 goes into 18 9 times, and I did not factor out an m, so I still have an m squared, and then I factored out the n. So again, we're thinking distributive property. If I multiply 2n by 9m squared, I'm going to get back to 18m squared n. Minus, I factored out the 2n, so I'm left with an n squared. You can also think exponent rules may be a way that you approach and think about factoring polynomials. Again, I can't show you every single method that you've ever learned. I'm trying to compile the ones that we use most often. And then looking at this last set, 9 is a perfect square of 3, And then I have an m squared, so I can write that as m. So I'm really just taking the square root of each of these terms. One is a plus and one is a minus, and the square root of n squared is n. And so this would be my entire final answer. And notice here again, even though I factored out that GCF of 2n, it doesn't disappear. It still has to be included in that final answer. Three terms, we're looking at those trinomials. When you learned how to factor trinomials, you were looking at things that multiplied to give you the first, like a times c, and then they had to add together to give you the middle term. So some of them had a coefficient of 1, and then some of them are going to not have a coefficient of 1. So if you look at this 30x squared minus 27x. So I'm going to need a little bit more room, so I'm going to work these two over here on the side of the screen. And again, you could have learned other strategies. I want you to use what you're most comfortable with. But I do know that most of our Math 2 teachers here at the early college use the x problem. So the c value goes in the top of that puzzle, and then the coefficient on our middle term goes into the bottom. So the question we're asking ourselves is, I needed two numbers that multiply to give me negative 42, that when I add them, I'm going to get negative 1. So the two factors of 42 that are 1 apart are 7 and 6. So you may have to do a little guess and check with these, but this one is one of our basic multiplication factors. So 7 times 6 will give me 42. Now I need to figure out the sign. So I need to have a negative 1. So the negative 7 plus 6 would give me a negative 1. So now I have my two factors that are adding together to give me that middle term. So again, we want to make sure that we think about this as we're taking that middle term and breaking it apart into those two x values. So we're going to set up our two sets of parentheses, x and x, and then we had a minus 7, and we have a plus 6. So again, if we took and multiplied all of that together, the first two terms together, the outside, the inside, the last two terms, we would get what we started with. So this is my final factorization of that quadratic trinomial. On that second example, we've got to look for GCF first. So 30x squared, 27x, and 6. And the reason I know I have a GCF is because all three of those numbers are divisible by 3. So just looking at that, I know that I'm going to have to factor out a 3, which would leave me with 10x squared minus 9x plus 2. Now, the coefficient on the x squared is not a 1, which means that when I do my little puzzle here, I have to take and multiply that 10 and the 2 together to make sure that I get the correct middle term. So 10 times 2 is 20, and then we put the negative 9 here. So I need numbers that multiply to give me 20, that when I add them, I get 9. So 4 and 5 are going to multiply to give me 20. But when I add them together, I need to get a negative, which means I need to make them both negative, because a negative times a negative will still result in that positive 20. But now when I add them, I'm going to get a negative 9. So the reason it's important to think about breaking those two things apart is because we can use the box method to help us finish factoring. So to do this, our first term of that quadratic is going to go in that first box. The 2 goes in the bottom right corner. And then these two factors, it doesn't matter where you place them in the boxes, but we're going to give each of them a box. So that is representing that polynomial inside that box. We've just broken it apart. After you have your boxes, then you take the GCF of each column and each row. The GCF of 10x squared and negative 4x is going to be a 2x. The GCF of negative 5x and 2 is 1. So if there's nothing larger, we still have to acknowledge that the GCF is 1. And then 10x squared and negative 5x, the GCF is going to be a 5x. And then the last row between negative 4x and 2, the GCF is a 2. Now what this means is that I should be able to multiply the number to the left and on top to get to the number in the box. So 5x squared and 5x and 2x give me 10x squared. But we have a problem because 2x and 2 would be a positive 4x. So I actually need to make this number a negative so that the multiplication works correctly with the sign. And then 5x and a 1, I need that one to give me the negative 5x. So now this is going to work because the negative 1 and the negative 2 is going to give me a positive 2. So by using that strategy, we actually have now got the two factors on the side and on the top of that box. But again, when I write the factorization, I have to make sure that I include the 3 that I factored out as a GCF so that I get the correct solution. You can also use guess and check. You may not like the GCF with the box, which is fine. Again, I want you to use whatever strategy it is that you learned in Math 2 that makes more sense to you, but that's just one that I like because it's very easy and clean to work with. I don't really like to do all the guess and check work. So the other strategy that we can use for trinomials is substitution. And we can use substitution when it looks like I have the quadratic trinomial, but I actually have x to the 4. So I have a higher degree polynomial. And so what this means is I'm going to say, well, I can think about this problem just like it's a quadratic. And so mathematically what we have to actually tell somebody is we're going to let x squared equal x. So we're kind of set like breaking apart. But what I think about is, well, if I had 2x squared plus 20x plus 50, I know how to factor that pretty easily. And it's going to be only slightly different. So it's almost like I'm kind of tricking my brain into seeing something I'm a little more familiar with. So I'm going to start by factoring out the GCF of 2. So I have 2x times x squared plus 10x plus 25. This is what we call a perfect square trinomial. If we go through the process of factoring, I end up with the same thing twice. So if you can identify some of those perfect squares, it's going to make your life a little bit easier. If not, you could have used the box method that we learned on the previous problem. But now that I've factored this, now I've got to go back here and I've got to say, well, I factored it, but I need to multiply this together and get x to the 4th. So those x's is where the substitution comes in. I'm going to change those back to x squared. And if we took and multiplied all of that out, we would get our x to the 4th that we need for that factorization. So substitution is not one that you use a lot, but I just wanted you to know that that is an option for factoring. But the strategies are the same as if we were factoring a quadratic trinomial. The last one is 4 terms. And when we have 4 terms in a polynomial and we're trying to factor, what we really want to think about is grouping. So can I make 2 groups that have their own GCF? Sometimes we may have to rearrange the terms. So remember with addition and subtraction, they're commutative. So I can move terms around so that I could group them to have a GCF. Most of the time, it's going to work out that we can just group the way that it's written. But grouping takes a little bit of work. It is one that you want to just kind of be able to see and work through in your head when you're trying to find those groups. So now that I've grouped them, so now I'm going to only work in that set of parentheses. So the first thing is, what is the GCF between 2a to the 3rd and a squared b? And so we would factor out an a squared, which would leave me with 2a minus b. And then I need to look at the second set. So 10a minus 5b, the GCF between those is just the number 5. There's no variables in common. So 10a divided by 5 is 2a, and 5b divided by 5 is b. So what we see is, and this is the entire goal of factoring by grouping, is that the term in parentheses should be the same. Because now what we're going to do is we're going to factor that out of each term. So if it has, remember, if it has that in common, I can factor it out of both. So I'm really factoring that term out of both of those terms in that polynomial. And then what I'm left with is a squared plus 5. The two numbers that are in front of those. And then you always need to check again to make sure that you can't factor this anymore, and there's no more GCFs to be factored out. A squared plus 5 is not a difference of squares. It's not factorable. 5 is not a perfect square. So this would be the final answer. But there are cases where you might factor by grouping, but then have to continue to factor more to get it completely factored. So again, there are lots and lots of strategies, lots of things that I didn't even talk about in the video that you can use for factoring. It just requires practice and continuing to work on the skill. So, as I give you things to work on and ask you to practice, if you're not practicing, you're going to be incredibly frustrated later on in this unit, and you'll be incredibly frustrated once you get to higher level maths, because factoring on its own is not a very helpful skill, but it is helpful when you're working more complicated problems. And if you can't do some of the easier skills, when you get to the harder things, it makes them feel that much harder. So keep working at factoring, ask questions, get for help, ask for help, and then I will keep giving you things to practice.